My name is Dr. Ken Gallardi, and today I digress from my planned schedule of videos dealing directly with the complete photon model that I've developed to comment on the wave-particle duality as applied to radiation, or as I prefer to present it, the macroscopic-microscopic duality. The wave nature is the macroscopic perspective, and the particle nature is the microscopic perspective. The difference is that when one is looking at the radiation as a beam consisting of a large number of photons, as compared to when one is looking at the individual photon itself. And my perspective is that it is only by looking at the individual photon level does one begin to understand what is actually occurring. This is analogous to treating gold as infinitely divisible, or recognizing that there is a limit to divisibility, and that limit is the atom. And we have learned that to understand gold, we need to include the atom in our discussions. Before I give 3 examples from physics, let me illustrate with a sports wave that travels around an arena after a great goal has been scored. You can watch it by searching on YouTube for massive Mexican wave. One can observe its amplitude and the speed at which this wave travels, as if it were a real wave, rather than recognizing that there is a limit to which you can divide the wave, and when you get to that limit, which in this case is the spectator, you observe a completely different picture. The individual simply raises or lowers their hands, which, when combined with what others are doing, gives the appearance of a wave, but in fact is far from being a wave. If you want to know what is actually happening, you have to look at the individual spectator sport level. Now the 3 examples from physics. First, consider a beam of linearly polarized radiation when it strikes a polarizing film as shown. The wave, or macro treatment, characterizes the beam by an electric field in the direction of its polarization that you can resolve into components without asking where the field comes from. And that beam can be subdivided so that one of the components is transmitted and one is absorbed. This macro picture gives the correct answer for the relative intensity of the transmitted beam, and you may be tempted into imagining that you're able to treat the photons like a cumulative vector, which in turn can be resolved into components. Essentially, this implies that the beam is infinitely divisible. But as you reduce the intensity of the beam to the point where you can distinguish a photon, you discover a totally different picture. You discover that the entire photon is either transmitted or absorbed, and you have run into the fundamental feature of the photon, which is quantization. Now, you can't predict if a particular photon will be transmitted or absorbed, leaving one to obtain the relative intensity that's transmitted by taking the ratio of the number of transmitted photons to the number in the initial beam. You get the same answer, but the explanation for what is happening is totally different. In the particle model, you deal with quantization, which is the primary property of the photons. In the wave picture, you use an electric field that the beam is presumed to have, which is treated as if it were infinitely divisible, thus circumventing both the impact of quantization and the real picture of what's happening. Second, look at when a beam of radiation strikes a double-slit experiment. One can treat the beam as a wave and draw diverging wavefronts beyond each slit and watch as these waves make new wavefronts that in turn strike the detection screen. The superposition of these waves is asserted to create the double-slit pattern. Another approach attempts to bridge the gap by stepping into quantum mechanics and considering as a wave function to present a much different explanation of the observed light and dark paths. In this approach, a photon follows a path which is a probabilistic choice of one of many possible paths in the electric field. These probable paths form the pattern. In dark areas, no photons are landing. In bright areas, many photons are landing. The set of possible photon paths is consistent with the path integral theory, with the paths determined by the surroundings, that is, the photon's origin point, the screen, the slit, and by tracking and summing phases. But if the experiment is done with a reduced intensity, one gets to the point where one observes individual points where a single photon lands on the screen as shown. And while these points appear with no apparent order, after a large number of such observations are made, These points create the diffraction pattern. In this picture, there is no need nor reason to believe a guiding electromagnetic field exists, for that would imply that a single photon emits a field that in turn guides it along a path which may zigzag from the slits to the screen. In addition, neither macro picture explains what is happening in the Fresnel zone, while the complete photon model that I have developed gives a clear and elegant treatment of what is happening. The single photon picture yields a very different perspective than the picture that tries to give an answer using a beam perspective. Third, consider Huygens' principle, which imagines that all points on a wavefront of light in a vacuum or transparent medium may be regarded as new sources of wavelets that expand in every direction as shown. This principle gives a good picture if you are looking at a beam of radiation, but if you choose to reduce the intensity of the radiation, you reach a point where you run into quantization. At that point, you understand that you do not get intensity in all directions, but rather you get a single photon going off in some direction. Quantization is the roadblock that prevents you from dividing the radiation into infinitely small pieces. The point I offer is that you will never understand what is actually happening until you decrease the intensity of the experiment to a photon by photon basis, because it is only there that you are looking at how the fundamental unit of radiation behaves and incorporates the fundamental characteristic of the photon, which is quantization. And of course, what is really occurring is what is occurring at the photon level. This leads to one other observation, which is that the superposition theorem, while it may be useful for a wave picture, is not valid for radiation at the photon level. You can use it when you're treating a higher intensity beam because really you're looking at an average property and not looking at the detail of what is physically occurring. The superposition theorem cannot be applied at the microscopic level because you can't add two photons together and get a third photon. That's a violation of quantization. Another point is that one can use the wave approach if the correct answer is all you want. But that approach has misled many into thinking it describes what is really happening. If you want to understand radiation, you must use the particle or photon model, and I take the opportunity to assert that the complete photon model that I proposed makes understanding all of these events straightforward. Well, thanks for watching. Please subscribe to this channel, and you'll be notified when I post my next video applying the complete photon model to the Poisson dot. And please pass this video series on to others, particularly those in the physics community. Thanks for watching, and God bless.